So now we've done 2 slits and then 1 slit, and so what happens if we go the other direction and have a lot of slits? This is called a diffraction grating and creates a very interesting pattern of basically just dots. So what you see here in the image is actually a 2D diffraction grating where we have lines going both directions. What I have to show you in class is just a single one where we end up with just points of light across a line, and I think they actually go the other direction. So they go this way. They're perpendicular to the screen. So the diffraction grating consists of many, many, many lines. So we talk about these in basically thousands of lines per meter. So the intensity of the pattern on the screen is a result of the combined effects from interference and diffraction. So what does this diffraction grating do is we have a lot of different sources for our wave, and so we have lots and lots of destructive interference where we only have a few areas where we have a maximum occurring. So now we're back to looking at the bright areas, and D is the distance between the slits. So D sine of theta is equal to m lambda, the exact same equation we did for a double slit. Doesn't really matter how many slits there are, we're just going to get a very different pattern. And here it's going to be easier to see where the bright areas are because they are basically just points of light. So the diffraction grating is, again, the center is going to be m is equal to 0. And the first order, so we go plus or minus 1 in integers, 1, 2, 3, 4. And the sharpness of the maxima, and we have a broad area of dark surrounding each maxima. This is a contrast to the single slit diffraction where we have very wide bright areas and very tiny dark areas. Okay, so let's look at how this works out mathematically. We're given that light of 650 nanometers, so that's our lambda, can be seen, and only 3 orders can be seen. So that means we have our central one, so our m is equal to 0, then m is 1, 2, 3, and then 1, 2, 3 on either side. So I have m is equal to 3, but I do not have an m is equal to 4. It's not visible. And why is it not visible? Is because these come out at an angle. I've not really shown this probably to scale, but that means that theta for my m is equal to 4 must be greater than 90 degrees to be non-existent. So we're basically bending light, trying to bend light farther than it can bend. It can only bend up to 90 degrees. So here is our equations. So this one, we can see, this one is no-go. We don't see that one at all. So we're going to use the m is equal to 3 equation. We get D, and we're going to put in 90 degrees kind of as a maximum. We're not going to get an exact number for our diffraction gratings because we don't have the exact measurement of the distance between each of our gratings. We're going to say that is equal to 3 lambda. And so if I solve that for D is equal to 3 times 650 times 10 to the negative 9th meters, all over my sine of 90, that's just 1. So we get D is equal to 195 times 10 to the negative 6 meters per lines. And typically diffraction gratings are measured in lines per meter instead of meters per line. So this is the distance between each line. We want to see how many lines there are per meter, so I just need to take the inverse of that. So 1 over 195 times 10 to the 6. Sorry, negative 6 should be in there. And I get 5,128 lines per centimeter. So here is all that nicely written out. Now we want to look, now it's your turn to look at a diffraction grating has 5,000 slits per centimeter and how many orders of violet light with a wavelength of 412 can be viewed. So remember, you want an integer. Okay, time to do the math. So again, we have 5,000 slits per centimeter and we need D should be in meters per line, so we need to take the inverse of that, so 1 over 5,000 slits per meter gives us 2 times 10 to the negative 6 meters per slit. So and then we can put that into our formula. D sine of theta is equal to m lambda. So m is equal to d sine of theta over lambda. D is equal to 2 times 10 to the negative 6 meters times the sine. Again, the maximum is 90 degrees. So 412 times 10 to the negative 9th meters gives us 4.85 millionths on that because it's just an integer. And so that means that any higher than this, that we will not observe. So that means the last one that's observed must be m max must equal 4 because 4 is visible, m is equal to 5, not going to be visible at all because it's bigger than 4. Here's all those values again.